Calculus, video 59, L'Hopital's rule. Alright, so for L'Hopital's rule, this goes back to limits that we were doing at the beginning of calculus. And you might be asking, well, why are we doing limits again? Now, halfway through calculus. The answer is this strategy for solving a limit, we couldn't do at the very beginning because it involves a derivative. But now that we know derivatives, we can go back and we can use L'Hopital's rule to solve limits that were maybe a little bit challenging for us in the beginning of the semester. So, specifically, recall limits in indeterminate form. Remember, indeterminate form is when we have like 0 over 0 or infinity over infinity. So if the limit ended up being 0 over 0 or infinity over infinity, we're going to be able to use L'Hopital's rule to solve it. If the limit is not 0 over 0 or infinity over infinity, you cannot use L'Hopital's rule. Okay, so some examples of some limits that we had previously in calculus are things like, what is the limit as x goes to 0 of the sine of x over x? Right, if we were to do some direct substitution, plugging in 0, we would get the sine of 0, which is 0, divided by 0, which is 0. And so this is 0 over 0. So that is an indeterminate form that we could use L'Hopital's rule for. Okay, take a look at number 2. This is another kind of a limit that we had previously. The limit as x approaches 4 of 1/4 minus 1 over x divided by x minus 4. So again, if we were to do direct substitution, plug the 4 in for the x, we'd get 1/4 minus 1/4, so that'd be 0 in the numerator. And 4 minus 4, that's 0 in the denominator. Again, 0 over 0, indeterminate form. We can use L'Hopital's rule in this. Okay, a couple other ones here. Same idea. The limit as x goes to 0 of e to the x minus 1 over x. E to the 0 is 1. 1 minus 1 is 0. X is 0. You get 0 over 0. Here we're letting, at number 4, letting x go to infinity of x squared plus 2x plus 3 over 4x squared minus 17. Now if x is going to infinity, x squared is infinity, plus 2 times infinity, plus 3, we get the limit goes to infinity over, again, infinity squared times 4 minus 17 is infinity. Also an indeterminate form that can use L'Hopital's rule. And finally, number 5 here, the limit as x goes to 1 from the right of the natural log of 1. The natural log of 1 is 0. And divided by 1 minus 1, again, 0. Again, indeterminate form. So as long as the limit goes to 0 over 0 or infinity over infinity, we can use L'Hopital's rule to solve it, as opposed to the algebraic ways that we solved this back at the beginning of calculus. Okay, so let's take a look at L'Hopital's rule. L'Hopital's rule says this. If the limit as x goes to a of f of x over g of x equals 0 over 0 or infinity over infinity, and let me pause there. This limit as x goes to a, this a right here, could be a real number like x goes to 0 or x goes to pi or x goes to 7, or that could be the going to infinity as well. So we're letting a be a real number or letting a here be infinity or negative infinity. All right. If that occurs, if the limit as x goes to a of f of x over g of x equals 0 over 0 or infinity over infinity, then L'Hopital's rule says this. That limit, the limit as x goes to a of f of x over g of x, is equal to the limit as x goes to a of f prime of x over g prime of x. What we're doing here is we're taking the derivative of the numerator, so the derivative of f prime, and the derivative of the denominator, g prime, and we're doing it separately. We're not doing quotient rule here. We're doing just the derivative of the numerator and just the derivative of the denominator. It's like the thing that I told you not to do at the beginning of the semester when you had a quotient, right? You can't just take the derivative of top and bottom. Well, this is a special case. We're talking about a limit of indeterminate form. You can just take the limit of the numerator, the derivative of the numerator and the derivative of the denominator, using the limit of that is the same thing as the limit of the original function f of x over g of x. That's L'Hopital's rule. Let's see how that can help us. So I'm going to go through those 5 examples that I have listed up here. And let's go ahead and start with the limit as x goes to 0 of the sine of x over x, which, if you remember, I wish I should have marked the video here. In one of the earlier videos, we did a proof of this. We did a proof of the limit as x goes to 0 of sine of x over x. And the proof was quite lengthy. I think that video might have been, I don't know, 20 minutes long or something. Involved the squeeze theorem and geometric shapes. We had like a triangle, which is smaller than sorry, lost the term there. The triangle, which is the smallest one, the sector of the circle was the medium one, and the larger triangle was the outside one. And we used the squeeze theorem to show that both sides, both larger and smaller, went to 1, therefore the middle one went to 1 as well. Anyway, it took us a while, but now with L'Hopital's rule, we can do this pretty fast. Okay, first of all, when you're doing this, you always want to try direct substitution first. So we're going to plug the 0 in here. We get, just like we saw before, the sine of 0 over 0. That is 0 over 0. So because it's of this form, I can do L'Hopital's rule. So L'Hopital's rule is okay to use. Okay, so we can, what we're saying with that check mark here, is we can use L'Hopital's rule. So let's do it. This then is equal to the limit as x goes to 0. Again, you have to write the limit each time. Okay, now we're doing the derivative of sine of x. Derivative of sine of x is cosine of x, divided by the derivative of x. The derivative of x is 1. Okay, so we've taken the derivative of the numerator and the derivative of the denominator, and now we're going to use direct substitution again. So we're letting x go to 0, so this is the cosine of 0 over 1. Cosine of 0 is 1 over 1, and we get an answer of 1. And we see that the limit as x goes to 0 of sine of x over x is indeed 1 using L'Hopital's rule. Okay, let's do another one. Number 2. Number 2 is the limit as x goes to 4 of 1/4 minus 1 over x minus 4. The limit as x goes to 4 of 1/4 minus 1 over x minus 4. I've already done the plugging in to get 0 over 0, but it's good to make sure we're using that each time. We're always trying direct substitution first. 1/4 minus 1/4 is 0. 4 minus 4 is 0. We can use L'Hopital's rule. So, can use L'Hopital's rule. To do so, we'll take the derivative of the numerator, the derivative of the denominator. So this is equal to the limit as x goes to 4. The derivative of 1/4 is 0, minus the derivative of 1 over x is negative 1 over x squared, over the derivative of x is 1, and the derivative of 4 is 0. Now, if you want to see the side work for the derivative of 1 over x, or in this case, negative 1 over x, recall that the derivative of 1 over x, that's the same thing as the derivative of x to the negative 1. All right, so to do that, we bring the negative 1 down, then it's x to the negative 2. That's the derivative of x to the negative 1, which we could rewrite as negative 1 over x squared. So you'll see that is where I'm getting this negative 1 over x squared. And honestly, the derivative of 1 over x, we use that so often that just knowing the derivative of 1 over x is negative 1 over x squared can save you some time without having to go through these steps each time, and just to know that that is negative 1 over x squared. All right, so if we have here, this is equal to plus 1 over x squared. So we have the limit as x goes to 4 of positive 1 over x squared over 1. Now let's go ahead and let x go to 4. And we get 1 over 4 squared. That is 1 over 16, which is the limit. Okay, so we like L'Hopital's rule. It speeds up our process for finding the limits in indeterminate form. Let's try another. Number 3, we have the limit as x goes to 0 of e to the x minus 1 over x. Now you may not have, we may not have done this one in a previous video because this one's a little bit more hard with the algebraic ways, but with L'Hopital's rule, it's not so bad. First of all, let's go ahead and plug in 0, do some direct substitution. I get e to the 0 minus 1 over 0. E to the 0 is 1, 1 minus 1 over 0, that's 0 over 0, so we can use L'Hopital's rule. Therefore, this is equal to the limit as x goes to 0. What is the derivative of e to the x? Well, that is just e to the x. The derivative of 1, that is 0. And the derivative of x is simply 1. So now we have this is equal to the limit as x goes to 0 of e to the x over 1, which is e to the x. That would be e to the 0, which anything to the 0 here is 1. Any real number to the 0 is 1. So, L'Hopital's rule. All right. 2 more here. Number 4. The limit as x goes to infinity, this time, of x squared plus 2x plus 3 over x squared minus 17. I'm sorry, it should be 4x squared minus 17. Did I have the 4? So yeah, 4x squared minus 17. All right. Now, if you remember, we actually had some rules that we used back when we first learned limits for this one. As x goes to infinity here, because the degree of the numerator is 2 and the degree of the denominator is 2, this is going to limit to the leading coefficients there. The coefficient on the x squared term, which is a 1 over 4. And we should know from previously that this should equal 1/4. However, we could also use L'Hopital's rule to solve this. So we're going to see that the answer here is 1/4, the leading coefficients, the 1 over 4 there. But if you just plug in infinity, you get infinity squared plus 2 times infinity plus 3, that is infinity. 4 times infinity squared minus 17, that's still infinity. So infinity over infinity is one of the 2 ways that we can use L'Hopital's rule, 0 over 0 or infinity over infinity. So what we can do is we can then take the limit as x goes to infinity, the derivative of the numerator, the derivative of the denominator. It's a good idea here, pause the video, work through this one on your own, see if you can find the correct answer here. Okay, so let's take the derivative of the numerator, that would be 2x plus 2 over derivative of the denominator would be 8x plus 0, so just 8x. Now, the reason I like this problem when demonstrating this is sometimes when you use L'Hopital's rule, as we've done before, we use it one time, we do direct substitution, and we're done. But sometimes when you use L'Hopital's rule, you'll do it once, you'll try plugging in direct substitution, like in this case, and you don't get an answer. You still have something in indeterminate form. If we were to plug in infinity, we get 2 times infinity plus 2 is infinity, and 8 times infinity is also infinity. This is still indeterminate form, infinity over infinity, so we can use L'Hopital's rule again. All right, so let's do it a second time. This is now equal to the limit as x goes to infinity. Take the derivative again, and you get 2. Denominator, derivative of 8x is 8. And now letting x go to infinity, well, there are no x's, so we just get 2 over 8, which simplifies into 1/4, which is the answer we got with the leading coefficients of the x squared over x squared term. All right, last one. Last one is the limit as x goes to 1 from the right, the plus sign, remember, is from the right, of the natural log of x over x minus 1. Okay. So at 1 would be the vertical asymptote. So we're looking at what happens, right, because you're dividing by 0 there, 1 minus 0. We're looking at what happens as x approaches 1 from the right-hand side. So let's go with, you plug in 1, you get the natural log of 1 over 1 minus 1. Natural log of 1, 0. 1 minus 1, 0. Right, we can use L'Hopital's rule, so let's try L'Hopital's rule here. Again, you can pause the video, try it yourself, unpause when you're ready to watch. This will equal the limit as x goes to 1 from the right. The natural log of x, its derivative is 1 over x, over the derivative of x minus 1 is 1. And now try some direct substitution. That's 1 over 1 over 1. That is just 1. Okay, so there's some examples of using L'Hopital's rule to evaluate limits that are an indeterminate form, 0 over 0, or infinity over infinity.